me see if it works. Just 1 second. Wait it up. Okay. Okay. So today we have Rodrigo Voivodic. He was a PhD student at the University of São Paulo, so he's a very close friend of mine. And now he's doing his postdoc at the Nostia International Center of Physics. And he's been doing works in modified gravity, halo, voids, all this sort of stuff. And now with the responses of halo occupation distributions that he will be talking to us today. So Rodrigo, thank you for accepting the invitation, and whenever you want to start.
Okay. Yeah, Carol, thank you very much for your invitation. It's a pleasure to be here. I would like to be there, but unfortunately it's not possible now, right? But okay, in this presentation, I want to talk about the response of the halo occupation distributions and how this response affects the halo model prediction of the galaxy bias, okay, in particular of the linear galaxy bias. So, okay, so what's the main result of this work? The main result is that the halo tracer connection, okay, or the halo galaxy connection, depends of the local properties of the fields, for example, of the density field or the gravitational potential. And this halo tracer dependence of the local properties of the fields will affect the linear bias of the tracer, even at very linear scales, okay, very large scales. So that's the main result here, and I will try to explain each point of this sentence. So I will start with a quick introduction to dark matter halos and what are the dark matter halos and how can we use the dark matter halos to constrain cosmology or to describe the distribution of matter in the universe. Then I will move to the halo tracer connection. So how we can use the information that we already have about halos to construct some information about one specific tracer. Then I will explain what are the response and what's the relation between the response and the bias parameters. Then I finally go to the results of the paper, starting with the measurements of the HOD response, and then how the HOD response affect the clustering of the galaxy and the clustering of the gas. Then I will finish with the conclusions. Okay, first of all, halos are just bound structures that are decoupled from the rest of the universe. So in some sense, they are a small universe that you can understand just the inner properties of the halos, and then you can just understand how the halos are distributed in the universe. So you can think about the halos in two different ways. The first of all is halos as biased tracers of the density field. So the halos are just a tool to describe the density field, okay? Just some intermediate step to really see the density field. And another way to think about halos are as the building blocks of the density field. So now, basically, the halos are the objects that construct the density field and not the opposite, okay? So I'll try to talk about the 2 points. Okay, first of all, as a biased tracer of the density field, we know that, for example, the density of halos is proportional to the density of matter on large scales. And this proportionality is given by the linear bias of halos. So the halo, basically, for example, the power spectrum of halos is just the power spectrum of matter multiplied by a number, which is, again, the bias of halos. In this sense, the halos are just tracers of the density field. Okay, another way to see the bias of the halos is not just as the ratio between the halo-halo power spectrum of the matter-matter power spectrum, but also as the response of the number of halos when we change some property of the underlying field. For example, B1, which is the same B1 that appears in the linear power spectrum, in fact, is just the derivative of the number of halos with respect to a long wavelength perturbation of the density field. Okay, so it's just a derivative. And in this figure here, you can see the number density of halos in the y-axis as function of the long wavelength perturbations of the density field. The different pinels are just different mass beams. And we see that this relation is quasi-linear for the low mass halos and more non-linear for the high mass halos. But the slope of these curves here are just B1, which is another way to understand B1. Okay, another way to think about halos is as the building blocks of the matter distribution in the universe. A very good model to do that is the halo model of Rgϕ and Rgσ. And the main idea of the halo model is just that all matter in the universe belongs to dark matter halos. So you can write down the density field for the matter just as the sum over all halos in the universe, which is given in this first equation here. When you do that, we see that for all correlation functions, we can split all terms as contributions between points inside the same halo and points that are in different halos. Okay, for the power spectrum, it's very clear because you can write the matter-matter power spectrum as the one halo, which is just the correlation between two particles in the same halo, and the two halo, which is correlation between two particles in different halos. For example, for the bispectrum, we also have some different mixtures of this kind of effects. Okay, but for the power spectrum, it's very simple. And here we can see that the one halo term, for example, only depends of the mass function of halos, which only gives the number of halos with a given mass beam, and the density profile of halos, which is this U function here. So the one halo term is basically the distribution of matter inside the halo, okay, which is the density profile of halos. And the two halo term is given also as an integral over the mass function, over the density profile, but also over the halo-halo power spectrum. So to compute the two halo term, which is much more important on large scales, we need to know the distribution of the halos in the universe, not just the distribution of matter inside each halo and the number of halos in the universe. So this is the general picture of the halo model.
Sorry,
and
here you go. Can I ask a question? On
yeah,
the
sure.
slide, what was U? Maybe you said it and I missed it.
Yeah, U is the density profile of halos. It's the normalized density profile of halos Fourier transformed. Okay, the Fourier transformed density profile of halos.
Okay, so something like an NFW profile.
Yes, exactly. Yeah. But U is normalized in such a way that when K goes to 0, U goes to 1. Okay.
Okay, thanks.
So the halo model has a lot of advantages. The first one is that we can describe the very non-linear scales. We can describe scales that are beyond the scales that for example, the perturbation theory breaks down. So you have a complete description of the matter distribution. The second good point about the halo model is that it is in principle a parameter-free prediction. Of course, you need to know how is the abundance of the halos, how is the density profile of halos, and also how is the correlation of halos. But we can, in principle, you can fit those expressions just using data for each expression. You don't need to fit directly the matter-matter power spectrum. Okay, so in some way, it's a parameter-free prediction of the matter-matter power spectrum. And finally, the halo model is also a very useful way to think about the matter distribution in the universe. And this third point, I think that's the main point for the rest of this talk, because you can also use the halo model to understand how tracers are distributed in the universe. Okay, so now moving on to the halo tracer connection. As I said before, it is based on the halo model. And the idea here is that all tracers belong to dark matter halos. So the idea that all galaxies in the universe, or all H1 in the universe, or all electrons in the universe, everything belongs to halos, okay? So in principle, if you assume that it's true, we only need to know two things, not two things, but two classes of things. The first one is how are the properties of the halos? What are the properties of the halos? Okay, and you need to describe the properties of the halos. And the second point is that we need to describe how the tracers are connected to the halos. Okay, and the second part is the most important one for this talk. So here, just to explain what I mean with tracers. Tracers might be, for example, galaxies. So I think that's the main application of this kind of things. But also H1, which is very important for 20 centimeter intensity mappings. Electron density, which is important for the Sonnai-Abzodovich effect. And also, I don't know, the density of other gases, which is important for other types of intensity mapping surveys, and also for Lyman alpha surveys. And basically everything that you can observe in the universe, you could in principle describe with this formalism of the halo model. Okay. So the first part, which is the halo properties, we can describe very well using N-bar simulations, especially using dark matter only N-bar simulations. The three main properties that we need to know is the halo mass function, which is just the distribution of halos with a given mass. We also need to know the halo density profile, and you can use, for example, NFW, which is a very nice description. And also need to know the correlation between halos, which is well described by just the linear bias of halos as function of the halo mass. And here I have just some plots to illustrate these three properties of the halos. And the dots are measurements from N-bar simulation, and the lines are different predictions. And you see that we have good predictions for all the properties. Okay, of course, there are a lot of things that we need to improve. For example, it's not so easy to predict those properties in modified gravity. It's not so easy to predict those properties when you have no primordial non-Gaussianities or neutrinos, or even baryonic effects, but in principle, you can just use simulations, okay? So the main problem is to understand the halo galaxy or halo tracer connection, okay? The first problem to understand the halo tracer connection is that it's really, really hard to simulate the whole universe with baryons and stars and black holes and everything. For example, we have some simulations like IllustrisTNG and others. Here is an example of the power spectrum coming from IllustrisTNG 300 for different types of matter. Okay, so we see that we have many types of matter. So you have to track those many types of matter in the N-bar simulation, and we also have to have a subgrid model to describe how those types of matter interact. Okay, for example, we need to know how we form a star given some density of gas in a cell in the simulation. And in principle, you have to have a lot of astrophysical models to describe everything. So one very useful way to not do that is to use phenomenological models. For example, to use the halo occupation distribution model. Okay, and the halo occupation distribution model basically tells how the galaxies are distributed in the halos, okay, which is the basic ingredient that we need now. And you can split this HOD models in three main ingredients. The first one is just the probability of finding any galaxy of a given type, okay, or I don't know, some mass of gas or something like that in a halo with a given mass. The second ingredient that we need is the density profile for the tracer, okay, which usually is but in principle is different of the density profile of the halos, okay. But usually the people just assume that is the same of the density profile of the halo, just NFW, for example. And the same for the velocity profile of the tracers in the halo, okay. In principle, they are different, but usually the people just assume that's the same of the dark matter halo. So in the end, we only need to know the PDF of having any galaxy in a given halo. Just to point out something here, which is important, is that in principle, those properties depends not just of the mass of the halos, but also of secondary properties. And those secondary properties that are very important to describe, for example, the Laurel spectrum of galaxies. And those secondary properties are also known as galaxy assembly bias. Basically, it's the fact that the bias of galaxies depends not only on the mass of the halos, but also on secondary properties of the halos, like the concentration or the assembly history of the halos. Okay, so it's very important for other studies. Okay, but again, the PDFs are usually assumed to be Poissonian. For this, usually we split the galaxy of a given halo in the central galaxy and the satellite galaxy. And the satellite galaxies have a PDF that is assumed to be Poissonian, and the central galaxy is just follow a PDF that follows the nearest integer distribution. So it's basically 1 or 0, right, for the central. But for the satellites, we can have any number. So if now we fix the PDFs, we only need to know the mean HODs, okay? Because the Poissonian distribution is completely determined by one single number, which is the mean, the PDF, and the same for the nearest integer distribution.
Great, Rodrigo, another question. Can you explain again what you meant by nearest integer distribution?
Yes, basically you have a PDF, which gives a number between 0 and 1, and you just generate a random number and see if this number is larger or smaller than the PDF. This number is 0 or 1. So basically we generate a number following the PDF, and if the number is larger than 0.5, it's 1, if it's smaller, it's 0. Okay, I don't know. Okay.
What is the shape of that PDF?
Usually it's like a R function. Okay, something that goes from 0 to 1 with a smooth transition. And basically you have two free parameters. One is this scale of the transition, and the other one is the slope of the transition between 0 and 1.
Okay, and that's 100% sure. What's that giving you then? That's giving you positions or just numbers of central galaxies?
Just numbers in this case, okay? Because the positions are given by the density profile of the halo.
I see.
So in the first step, you just say how many galaxies you have in each halo. In the second step, you give a position for each galaxy following the density profile. And the third step, you also give a velocity to each galaxy.
Okay, so just to check I've understood, so if you want to sort of input, you want to calculate, you want to create the number of central galaxies for a given halo, you have some parameters that control this this smooth step function that's your, and then so with your transition, the center and the width, and then you draw a sample from that, and that either becomes a 0 or a 1, and then there's some number that which then scales that into a number of galaxies.
For this case, just the number of central galaxies, right? Which is just 0 or 1. But to also have the satellite galaxies, which follows a Poissonian distribution. The central galaxy, sorry?
I'm not sure I understand what you mean that the number of central galaxies is 0 or 1. Isn't it a number like, how do you get a number like 50 or 30 or 100 out of that?
Yeah, this comes from the satellite galaxies, okay? You can only have one central galaxy.
Oh, I see. Okay, sorry, beg your pardon. I was thinking there was a group of central galaxies. Okay.
Yeah, maybe I have here, not so clear, but yeah, this like where we split the mean HOD in central satellites, okay? So you have an expression like this. I don't know if can you see my
yeah,
arrow? Yeah. Okay. I have an expression like this, and this first guy here follows this nearest integer distribution, and the second guy follows the Poissonian distribution.
Sure.
So the first guy is 0 or 1 for a particular halo, okay, and the second might be any number, basically any integer number. Yeah.
What does it mean if the first number is 0? There isn't a central galaxy?
There is no central galaxy.
Okay. Okay. Got it. Thank you very much.
Yeah, you're welcome. So yeah, okay. So the conclusion here is that in the end, we only need to know the mean number of galaxies per halo. Okay, we don't need to know the distribution of galaxies in the halo because we just assume that's the same of the matter distribution in the halo, and the same for the velocities. And we also can just fix some PDF. So we just need to know basically one function for the centrals and one function for the satellites. Okay, of course we can change these assumptions. For example, we can change the PDFs, and this will change a little bit for example, the galaxy per spectrum, but the effects are very small, and usually they are not very important. For example, the secondary properties are more important than the PDFs of the HODs, okay, usually. So here is just some examples of some HODs or mean HODs, okay? Sometimes I will say just HODs, but I want to say mean HODs, the mean of the HODs, okay? But here we have measurements from IllustrisTNG, okay? Both for IllustrisTNG 300 and IllustrisTNG 100. The different colors are the different simulations. The different pinels are different redshifts. And the different line styles are different cuts, the stellar mass of the galaxies. And basically, you will see that if you do a smaller cut, like the dashed line, we have galaxies even in the low mass halos. But if the mass of the galaxies are larger, we have galaxies just on the more massive halos, which is very logical, right? Of course, I cannot have a galaxy with mass 10 to 13 in a halo with mass 10 to 11 because the galaxies are inside the halos. We also have something here which is interesting, is in the comparison between the solid lines. The solid lines have the same cut, but they are from different resolutions of the simulation. And we see that they do not agree very well. And this happens because, again, it's very hard to describe these astrophysical processes and the baryonic effects in this kind of simulations. So our results should take each into account. So we can do basically the same thing, but now not for the number of galaxies in a halo, but for the total mass of a given gas in the halo. And here is basically the same type of figure, okay? But now I'm showing in the dashed lines the hydrogen, the solid lines the carbon, and the dotted lines the oxygen. Again, for the two simulations. And yeah, we see that we have a very different behavior, but as before, is something that increases the halo mass, which is expected, right? Because if you have a larger halo, we expect to have more gas inside the halo. So this is just to say that we can use the same formalism both to describe galaxies and gas. And you could also use to describe the electron density, for example, to use for Sanaev-Zadovich surveys, or not surveys, but surveys that want to measure Sanaev-Zadovich effect. Okay, now going back to the halo model, but with galaxies, we can modify the 1 and 2 halo term to predict the galaxy-galaxy power spectrum and not the matter-matter power spectrum. Now, basically, the 1 and 2 halo term will be changed, and that factor of the mass of the halos that we had here, okay, basically mass over the mean density of the universe that you had in both terms, now becomes the mean number of galaxies divided by the mean number of galaxies in the universe. Here's the mean number of galaxies in a halo with this mass that is integrated over, okay? Here, I also made the approximation that the halo power spectrum is just the bias square times the linear matter power spectrum. Okay, so you have this expression here, and in particular, in the limit of very, very large scales, with k going to 0, we can compute the P1, the linear bias of galaxies, in terms of integral over the mass function of the halos times the mean HOD times the bias of the halos. So the bias of the galaxies is just a weighted mean of the bias of the halos. And this weight is given by the number of halos times the number of galaxies inside each halo. Okay. And this expression will be very important. So now just slightly changing the idea, we can also consider the galaxy not using this explicit halo-galaxy connection, but using the bias expansion. And the basic idea of the bias expansion is that we can write the density of any tracer. Okay, again, it also is, you can also apply this for any tracer, but you can write this density as the sum over all relevant operators weighted by a number, and this number is the bias of a given operator. So in general, we have, for example, the linear density field, which is the most common term in this expression. You can also have some higher orders operators of the density field. You can have some other scalars of the tidal field, okay? Just remember that the delta is also a scalar of the tidal field, but we can also have different scalars. We can have non-local operators that are used to describe the non-local process of formation of mainly of the galaxies, okay, because galaxies have a size, okay, so they are affected by not by the point that the galaxies are, but also for the neighborhood. And you can also have, for example, the perturbations in the primordial gravitational field that just are relevant if you have primordial non-Gaussianities. You can also have things like compensated isocurvature perturbations which are perturbations in the baryon density field that are compensated by the cold dark matter field. Okay, so are basically perturbations that have delta equal to 0 because they just cancel out, but they are perturbations in both fields. And you can also have the stochastic terms that just accounts for small scale effects that do not correlate with the other fields here. Okay, so we have a lot of bias parameters, in particular at linear order, which is the order that we stop this work. We have just these 3 operators here. Of course, we also have the stochastic operator, but we will not account for it. It's not important. And as we saw before, the bias parameters are just derivatives of a given quantity with respect to the operator computed when the operator is equal to 0. So P1, for example, is just the derivative of for example, the number of galaxies in a given redshift divided by delta, the same redshift, computed when delta is equal to 0. Okay. And again, just generalizing the other expression using the Halo model, the bias can also be computed as the weighted mean of the bias parameter of the halos of the same operator times the HOD times the mass function. Okay, so it is in principle the general expression for any linear bias of any tracer. Okay, but now moving on to the HOD response. The whole point of the HOD response is that now we can consider that HODs, or the mean HOD, is not a global quantity that gives to you the number of galaxies for a given halo with a given mass, but actually it's a local quantity. So this number of galaxies also depends where in the space you are. So you can do the same bias expansion of this HOD, and now you have these bias parameters that you can also call just response of the HODs with respect to each operator. So in the same way we have defined it for the bias of the tracer, we can also define the response as the log derivative of the mean HOD with respect to each operator computed when the operator is equal to 0. Okay, and again, the main idea of this response is that they have information about this local dependence of the HODs. Okay, so the idea now is how to measure the HOD response. To do that, we use this method, which is called the separate universe simulations. Okay, the idea is to generate a universe simulation with a long wavelength perturbation of a given field. For example, to compute B1, we need to have a long wavelength perturbation in the delta field. So our whole or density field of matter will be shifted by this number delta L. And the same for PNGs, where you need to shift the amplitude of the primordial perturbations, and for the CIPs, the compensated isocurvature perturbations, where you need to shift the baryonic density field and also the cold dark matter density field by the same amount. Okay, and the idea of the separate universe simulations is that the local structure formation in long wavelength perturbations is the same of global structure formations with a modified cosmology. So we can basically remap this. We can map this change in the background of each field in a change in the cosmology. Okay, and doing it, we can directly compute the response, because the response are just derivatives, and the derivatives, when you do just a finite difference, it's just basically this expression. You just need to compute the number, for example, the number of galaxies, the total number of galaxies, okay, the box, for some separate universe simulation, divided by the total number of galaxies in the fiducial simulation that have the long wavelength perturbation equal to 0, and just compute this ratio here, -1, okay, and divided by the operator or the perturbation, the field, because we are computing the log derivative, okay, so we have to have this term here, actually this term here of the fiducial. And we generated 2 separate universe simulations for each field, one which is called the high, and the other that's called low, which are just perturbations with a positive or negative value. Okay, just being more explicit. So you have the fiducial cosmology here in the first line with the cosmological parameters. Then if you want to compute this high delta M, which is just basically the same simulation, but with a positive long wavelength perturbation in the delta field, we can reobserve this change in the background as a change in the cosmological parameters. Particular change, we need to change omega n, omega b, omega c, omega lambda, and h. And we also need to change the physical. The main problem here is that the physical size are also changed because h is changed. So we also need to simulate the same box, but with a different size, and stop at different redshift to have the same physical time and physical size. And for example, for high and low AS, which are the simulations that we use to measure the primordial non-Gauss, the bias parameters that comes from the PNG, primordial non-Gaussianity, we just need to change the amplitude of the scalar perturbations. And for sigma, we just need to change omega b and omega c in such a way that omega n has the same value, okay, which is the idea of the compensated isocurvature perturbations. So here is the figure, you can see the idea. We have these long wavelength perturbations. Then we assume that we have a box that is much smaller than the frequency of this perturbation. So the perturbation in the box is just constant. Okay, so you can do this approximation. Okay, we did it in the Illustris simulations, which is any-bar simulation with hydrodynamic effects and also astrophysical effects. We actually use it. Yeah, we use the TNG 100 and TNG 300, both the version with baryons and the version with long dark matter. And we also use this box with 212 megaparsec over H, but just for the case of dark matter only, okay, just with dark matter. So we ran 7 new realizations for each resolution, okay, because we need to have the fiducial, high and low for the three fields. So we have a total of 7 simulations with the same seeds. And we have a 1250 dark matter particles and 1250 baryonic particles, okay? And we have outputs in 5 different redshifts. So, okay. Using these, we can explicitly compute the derivatives, so you can explicitly compute the response. First of all, we compute the response with respect to, here are just some examples, okay, with some selected redshift and operators. Each column is for each operator. And we have the response as function of the halo mass for the 2 simulations. And here is the response of the mean number of galaxies selected by the total mass of the galaxies. Okay, because in principle we can make different cuts in the galaxy, and if you choose to do the cuts in the total number of galaxies, we see basically a zero response. So the responses are completely negligible here. But if you select the galaxy by the stellar mass, not by the total mass, we see that the response with respect to delta is basically zero. Okay, the regions here, the green and blue or purple regions, are the regions where the range of mass where the halo model integral is higher. Okay, so the HOD times the abundance is higher in these regions here. So it is the most important region in the computation of the bias. And you see in the second and third column that for the case of the response with respect to sigma and phi, the responses are non-zero. So we actually have a detection of the response for these two cases. And you have very similar results for the gas. The response with respect to delta are basically zero, but the response with respect to sigma and phi are non-zero. Okay, but now the question is how this response affect the prediction of the bias of the tracer. And we can basically use again the halo model prediction. Okay, here this integral is the halo model prediction for the density of a given tracer. For example, for galaxies, the number density of the tracer. So the bias is just the derivative of this quantity with respect to the operator that we need to compute the bias. But now, if you assume that the responses are non-negligible, we see that in the final expression, we have actually a weighted mean of the halo bias times the HOD response. So we have this contribution of the HOD response even for the linear order of the bias of the tracers or the galaxy bias. And here is the comparison. Okay, so we have basically each column are different operators. Each line, each row are different cuts. Okay, for example, cut in 10 to 11, 10 to 12, and 10 to 13. The different colors are the different resolutions of the simulation. The dots are the direct measurements from the simulation. The solid lines is the halo model prediction without the response, and the dotted line is the halo model prediction with the response that we measure the same simulation. So here again, for the case when we selected the galaxy by the total mass of the galaxy, we see that the halo model with and without and the measurements are basically the same. It is because the responses are basically zero. But for the case of the galaxy selected by the stellar mass, we see that it's not the case anymore. We have basically the same results with respect to the operator delta, but not the same results with respect to the operator sigma and phi. So if you want to use this halo model prediction, for example, to constrain primordial non-Gaussianities or some models of inflation that predict some compensated isocurvature perturbations, for example, models with more than one scalar field, we need to take into account the HOD response. They are very important in the modeling of the bias of the tracer. And the same for the gas. For example, if you want to use, I don't know, the H1 to constrain PNG, you have to take into account the response of the H1 to perturbations in phi. Okay, so this is the main result of the paper. And here just we try to explain why you see this non-zero response for the galaxy selected by the stellar mass, but we didn't see non-zero response for the galaxy selected by the total mass. And the point is that the response, again, is just the derivative of the number of galaxies, okay, the mean number of galaxies, but the mean number of galaxies with stellar mass higher than some threshold, some minimum mass. And this HOD here can be just computed as an integral over the stellar mass, okay, of the basically the distribution of the stellar mass of the subhalos. And this quantity can be write as the integral over the total mass times the stellar to total mass relation. So you have an expression like this for this specific HOD. And from the first results, we know that the derivative with respect to each operator of the total number of galaxies selected by the total mass of the galaxy is basically 0. So the explanation is that this non-vanishing response is coming from a non-vanishing response of the stellar to total mass relation to sigma and phi. And this result is very similar to the result that Alexandre Barreira found here, where he computed the response of the stellar mass in halos with respect to two operators, in this case, to the operator phi and delta. And he found, that the response are actually 0 with respect to delta, but they are non-zero with respect to phi. So, in fact, the non-vanishing response are coming from the response of the stellar to total mass relation. And to finish, we tried to fit, just using some polynomials to fit the response, okay, of the galaxies, of the HODs for galaxy and gas, in this case for the galaxies, with 0 first and second order polynomials, and we checked if it was enough to describe the bias of the galaxy in this case. And we saw that using a 0 order polynomial seems to be already a good description of the HOD. So just a constant, an extra constant, is enough to go from the solid line, which is the halo model without the response, to the dashed yellow line, which is the halo model with this 0th order polynomial fit. Okay. So yeah, basically that's all. And again, the main conclusion is that the halo-trace connection depends of the local properties of the universe, of the fields, and this dependence is very important if you want to model the bias of a given tracer. It works both for galaxies, for a particular gas, or for anything else. Okay, yeah, thank you.
Thank you, Rodrigo. Are there questions?
No other way but a question. Rodrigo, thanks for that. That was really nice. So if I've understood correctly, to